Have you ever stopped to think about the absolute paradox at the very heart of our existence? Today, we're going to dig into what makes the element carbon so special, so fundamental, that it literally forms the backbone of all life as we know it.
So, let's kick things off with a simple question. If I asked you to name the single most important element for life, what would you say? Oxygen, maybe? Hydrogen? I mean, both are fantastic answers, but the real star of our show today is carbon, and the reason why is way more fascinating than you might think.
To really get it, first you have to appreciate just how incredibly rare carbon is. Get this, only 0.02%. That's the teeny tiny fraction of the Earth's crust that's made of carbon, in minerals, coal, and petroleum.
And it's not much better up in the air either. The atmosphere has only 0.03% carbon in the form of carbon dioxide. So we're talking about an element that's really just a trace material on our planet.
And this, right here, brings us to the big paradox. How on earth can this scarce element be the foundation for practically everything? I'm talking food, clothes, medicine, books, even us. Every living thing is built on a carbon framework.
So, let's dive into this paradox. We're going to look at the unique properties that let this rare element build a huge and complex world of organic chemistry. All right, the first clue to solving this whole mystery isn't about what carbon has, but what it does with what it has. It all comes down to a unique strategy for making connections, a secret of sharing. You see, most elements form what we call ionic bonds. You can think of it like a transaction. One atom gives up an electron and another one takes it. Simple. This creates charged particles that stick together. But carbon plays a totally different game. It doesn't give or take, it shares. And we call this covalent bonding. So why sharing? Well, a carbon atom has 4 electrons in its outer shell. To be stable, it really wants a full shell of 8. Now, trying to gain 4 more electrons would be super tough. Its nucleus just isn't strong enough to hold on to all those extras. And losing all 4, that would take a massive amount of energy. So the most efficient solution is to share its 4 electrons with other atoms, forming these incredibly strong and stable covalent bonds.
And carbon isn't just a one-trick pony. It can form a single bond by sharing 1 pair of electrons, a double bond by sharing 2 pairs, or even a triple bond by sharing 3 pairs. This incredible versatility is a huge reason it can form so many different kinds of molecules.
This amazing ability to form strong, versatile bonds gives carbon 2 distinct properties that are basically its superpowers. And these 2 abilities, working together, are what allow for the immense diversity of life we see all around us.
Superpower number 1 is catenation. It's a fancy word, but it just means carbon has this unique ability to link up with other carbon atoms over and over and over again to form long, stable chains and rings. Now, other elements like silicon can kind of do this, but nobody, and I mean nobody, can do it like carbon. The carbon-carbon bond is just exceptionally strong and stable, which is the secret to building the huge, complex molecules that life depends on. And carbon's second superpower? Tetravalency. Tetra just means 4. Because it has those 4 outer electrons to share, it can form 4 separate covalent bonds all at the same time. This turns every single carbon atom into a kind of universal connector. It's the perfect building block for creating complex, 3-dimensional structures. You can see catenation in action right here. We start with methane, just 1 carbon atom. Link another one to it, and boom, you get ethane. Add a third, you've got propane. This chain can just keep on growing, creating this huge family of compounds we call hydrocarbons. Now, thanks to these 2 superpowers, carbon isn't just stuck making straight lines. The architectural possibilities are almost endless. Let's check out the 3 main ways carbon builds the skeletons of molecules. So, like we saw, carbon can form simple, straight chains, but it can also create branch chains where new chains split off from the main one. And it can even loop back on itself to form super stable rings. Each of these different shapes creates compounds with totally different properties. This is a perfect example of something called isomers. Take a look at butane. Both of these structures have the exact same chemical formula, 4 carbons, 10 hydrogens. But because the atoms are put together differently, one is a straight chain, the other is branched, they're actually different compounds with different properties. Same parts, different blueprint. And then you have rings. In a compound like cyclohexane, the carbon chain literally connects end to end, forming a stable circular structure. This just adds another whole layer of complexity and variety to the types of molecules carbon can build. It's incredible.
Okay, this is all fascinating chemistry for sure, but how does it actually connect to our everyday lives? Let's look at a couple of examples where carbon's unique powers are at work for us all the time.
First up, fuel. Almost all the major fuels we use, coal, petroleum, natural gas, they're all carbon compounds, and when they burn, they release a ton of energy. Ever wonder why a gas stove has a blue flame, but a candle flame is yellow? It's because saturated hydrocarbons, like the stuff in natural gas, tend to burn really cleanly. But if the combustion isn't complete, you get that yellow, sooty flame. So here's a tip. If the bottom of your cooking pot is turning black, it probably means the air vents on your stove are blocked and you're actually wasting fuel.
Now, let's talk about something we all use every single day. Soap. The magic of soap is all thanks to a special kind of carbon-based molecule. It has this long carbon chain tail that hates water but loves oil, and then it has a head that loves water. They cleverly arrange themselves into this structure called a micelle.
So how does it work? It's actually a brilliant four-step process. Most dirt is oily, right? And oil and water don't mix. So first, the oil-loving, or hydrophobic, tails of the soap molecules dig into the greasy dirt. Meanwhile, the water-loving, or hydrophilic heads, stay on the outside, facing the water. This forms that micelle, a tiny little sphere that has the dirt trapped right in the middle. Finally, when you rinse, the water grabs onto those friendly heads and just washes the entire micelle away, taking all the dirt with it.
And you can see it right here. The soap molecules are completely surrounding the particle of oily dirt, lifting it right off the surface of your clothes. They form a perfect little transport pod that can be easily carried away by water. It's an elegant piece of chemistry happening every single time you do the laundry.
You know, to sum it all up, this quote from our source material really says it best. Carbon is the ultimate versatile element. Its unique properties, tetravalency and catenation, let it form the millions of compounds that build our world and our bodies.
We've seen how it makes life possible, how it fuels our world, and even how it cleans our clothes. From the hardest substance we know, diamond, to one of the softest, graphite, to the CO2 we exhale with every single breath, carbon truly is the element of life. It really makes you wonder, what other profound and hidden roles does this seemingly simple element play across the rest of the universe?